When we argue or reason, we use logic, well, at least when making correct arguments. Here is a simple sample argument. Let's say A and B are variables that have a numeric value, and we know that A is greater than 0 and B is greater than A. These are our premises, that is, the knowledge that is given and which we assume to be true. Knowing that A is greater 0 and B greater than A, we can conclude that B is greater than 0. Note that the conclusion is based on the premises. That is, the conclusion can only be made if the premises hold. If the premises don't hold, the conclusion may or may not hold. The premises together with the conclusion are called an argument. An argument consists of two parts. First, a premise, or possibly several premises. Let's call the premises P1, P2, P3 up to Pn. So we have n premises. Secondly, the argument consists of the conclusion that can be derived from the premises. Say the conclusion is a statement S. The actual argument is implication P1 and P2 and P3 and so on up to Pn implies S. An argument is valid if the conclusion is true whenever all premises are true. Formally, an argument is valid if and only if the implication P1 and P2 and P3 and so on up to Pn implies the statement S is a tautology. In other words, if and only if the conjunction of all premises logically implies the conclusion S. Often the premises are not explicitly stated because they might be well known or they are taken for granted. Note that not every argument is valid. So in order to prove that an argument P implies S is valid, we have to prove that P implies S is a tautology. As an aside, I occasionally overhear somebody saying something like, "Oh, I'm pretty good at math, but I'm not so good at doing all those proofs." Well, doing a proof is nothing else than showing that an argument is correct. Okay, so how do we prove that a given implication, P implies Q, is a tautology? If we are living only in the world of propositional logic, we have the following options. We can create a truth table for the implication and check out all possible truth values that the implication can have. If it evaluates the true in all cases, then it is a tautology. Keep in mind that a truth table will be very large if the argument contains a lot of logic variables. For example, if the argument has 10 logic variables, then the truth table has already 2 to the 10 rows, which is about 1000. Creating a truth table by hand is only practical if the number of underlying logic variables is small. The second option is the use of equivalence transformations. We can transform the implication until we find that it is equivalent to the truth value true, and hence the argument must be a tautology. Again, this is often not practical. In many cases, the number of premises is very large. In turn, the implication representing the argument becomes a huge expression, and transforming the whole expression becomes tedious. You're familiar with those first two techniques, and you have learned to create a truth table or to transform a logic expression. Well, at least I hope so. Another option to prove an argument is deduction. Deduction is the most commonly used technique. We will have a closer look at it. Deduction is a step-by-step process where we deduce new statements from some of the premises. The new statements that are deduced can then be used like a premise. That is, we can now deduce more statements using the original premises and the statements we have just deduced. The goal is to eventually deduce a conclusion S. The advantage of that approach is that in each step we can work with a few premises only. Here's an example argument that we can prove using deduction. The argument is based on the following four premises. The first one is, if I visit the Grand Canyon, I will see the most amazing sights of the world. Second, but if I do not visit the Grand Canyon, and if I do not see the most amazing sights of the world, my neighbors will not be impressed. And the third premise is, I have not seen one of the most amazing sights of the world. And fourth statement is, my neighbors act as if they are impressed. The conclusion is the following statement: my neighbors are only pretending to be impressed. Now let's prove the conclusion using deduction. Have a closer look at the first and third premise. Premise 1 says that I will see the most amazing sights if I visit the Grand Canyon. And premise 3 says that I have not yet seen the most amazing sights. So we can deduce that we have not visited the Grand Canyon yet. I'm lacking space on my slides, so I stick the statement in the upper right corner. We can use the statements we just deduced now like any other premise. Based on premise 3 and the newly deduced statement, we know now that we have not visited the Grand Canyon and that we have not seen the most amazing sights of the world. Due to premise 2, this implies that my neighbors will not be impressed. So now we know that my neighbors are not impressed. Again, I'm short of space and squeeze the statement in the lower right corner. Now we know that my neighbors are not impressed, but due to premise 4, they act as if they are impressed, so they are only pretending to be impressed. So we have finally deduced the conclusion. In this proof we have used several so-called inference rules of propositional logic. These inference rules help us to deduce new valid statements from given statements. If you have to prove an argument, you will probably apply some of the inference rules. However, note that in a practically useful proof, you will also use other rules and other types of argumentation. For now, we just stick to the limited world of propositional logic to learn and focus on the tools that propositional logic provides. Inference rules are basically valid arguments that serve as a template in many situations where you have to reason. We will go through a list of useful inference rules. Don't be put off by the formal way of describing the rules. Most inference rules are actually nothing else but common sense. So the inference rule modus ponens says that if we know P implies Q and we know that P holds, then Q holds as well. As far as the notation is concerned, we list the premises above the horizontal line and the conclusion below that line. Here's an example for modus ponens. Assume we know that if it is raining, the street is wet. And then we look out of the window and we observe that it is actually raining. So then we can conclude that the street is wet. Modus tollens says that if P implies Q holds, but not Q, then not P can be deduced. For example, let's say as before that we know that if it is raining, the street is wet. And we look out of the window and we notice that the street is not wet. Then we can conclude that it is not raining. The hypothetical syllogism says that if P implies Q and Q implies R, then P directly implies R. For example, I know that if I go to the Oktoberfest, I will drink a mug of beer. If I drink a mug of beer, I will not be able to drive home. So you can conclude that if I go to the Oktoberfest, I will not be able to drive home. The disjunctive syllogism says that if we know that P or Q, or both, must hold, and we know that P does not hold, then Q must hold. For example, let's say I decide to go to the gym today or to have a walk today. And then I decide not to have a walk since it's raining. Then you know that I will go to the gym today. The addition rule says that if P holds, then P or Q holds as well. This seems to be somewhat odd. Note that Q actually does not relate at all to the premise, but sometimes it is useful to add another statement by the means of a disjunction. For example, if we know that a fish is cold-blooded, then it is also a fact that a fish is cold-blooded or a bird is cold-blooded. And note it doesn't matter whether the bird is cold-blooded or not. This is a true statement that can be deduced. The simplification says that if P and Q holds, then P holds as well. For example, if I know that variable A is equal to 2 and variable B is equal to 3, then obviously we can conclude that variable A is equal to 2. The last two inference rules to look at are the conjunction, and then we'll look at the resolution. Conjunction means that if P holds and Q holds, then the conjunction P and Q holds. And resolution says that if P or Q holds and not P or Q holds, then Q or R has to be true. For example, let's say I have some shopping to do. Since I need to get a prescription drug, I go to Walgreens or I go to CVS. I also need to get some fresh produce, maybe at Kroger or Publix or some other store. I will not go to both Walgreens and Publix, let's say, as the two stores are at very different locations in the city. So I know that I will not go to Walgreens or I will not go to Publix. Then you can conclude that I will go to CVS or I will not go to Publix. Note that the statement P corresponds going to Walgreens and that the statement R corresponds to not going to Publix. So if we reason, then propositional logic provides us with two important tools. We can use the inference rules and we can use logical equivalences to transform an expression. In deductive proofs, we often use both tools, not just inference rules. There are some commonly made arguments that are invalid. Here's an example. Assume we know that if you have passed CS2, you are proficient in programming. Assume further that you are proficient in programming. One might be tempted to conclude that you have passed CS2, but this is not a valid argument. There might be some other scenario where both premises hold, but the conclusion that you have passed CS2 is false. Here's another common pitfall. Assume again the premise is that if you have passed CS2, you are proficient in programming. But we know now that you have not passed CS2. One might be tempted to conclude that you are not proficient in programming. But again, this is not a valid conclusion. Even if the premises hold, you still could be proficient in programming.